Hey everyone, in this video, let's take a look at question 76, minimum window substring on Leetcode. This is part of our blind 75 list of questions, so let's begin. In this question, we're given two strings, s and t, of lengths m and n respectively, and you want to return the minimum window substring of s so that every character in t, including duplicates, is included in the window. If there is no such substring, we return the empty string, and the test cases will be guaranteed so that the answer is unique. Okay, so let's take a look at what this is saying through our examples here. Go ahead and paste the examples. Okay, so let's take a look at the first one. So we have two strings. We have the string s and we have the string t. We essentially want to form a substring of s such that it contains all of the elements in t, including the count, including the respective count of them, and it is the minimum window substring possible. For example, we can see that this substring here is a valid solution, right? Because it contains the a ones, it contains the b ones, it contains the c ones. So this is a valid solution. But notice that it's not the minimum one. The minimum one is actually all the way here at the end, B, A, and C. And we can see that it also contains an extra element here, N. So that's fine. It doesn't have to contain, it doesn't have to be the string exactly. But notice here that it is the smallest window possible. So let's take a look at how we can maybe go about solving this question. And first thing you might notice is the minimum window, right? So whenever you see this window, you kind of want to think of a sliding window type approach. And sliding window might actually make a lot of sense here because maybe we can consider that this is the best window and then we can see that this is a valid window. So what it means is that anything after this will still be valid. But then if this is a valid window, why don't we maybe try to shrink it and see if we can find a better window and go from there? And so this is how we can go about doing this question. This is quite similar to one of the questions we did before, which was, I believe, similar questions. Maybe it was, I think it was minimum window without repeating characters, something like that. So it's just a video we did before this. So let's take a look at how we can maybe solve this question. Before I do that, let's just go to these other two examples. So here, s is equal to a, t is equal to a. It's exactly the same. So we can just return a, which is, and notice here, we're actually returning the string here. So that's one thing to notice. Here, it looks like a and aa. So you might think this is valid, but notice that here, a occurs twice, and here, the window only has one a. So actually, we can't form any window. So that's why it's empty here. Okay, let's take a look at how we might be able to solve this problem. And one thing I think that is obvious is that when we are forming our substring or a window in S, when we are forming this window, and by the way, for the sliding window type question, I've already done the question before of the find the smallest window without repeating characters. So that one, we already laid the foundation of how to do these sliding window type problems. So I'll be going a little bit faster in this video, just assuming you know like the basics of how to create a sliding window. But let's go ahead and run through this example to see how we might be able to do this. Well, okay, so first of all, we notice that in T, right, we have A, B, C. So when I'm forming my window here, I need to basically check, right? Like I need to basically check if like this D exists in T, if A exists in T, if B exists in T, etc. Not only do I need to check that, but I also need to check the count, right? Because, for example, if there was two A's here, then I need to make sure that this A accounts for one of them, but then I also need like another A somewhere else. So given that we need that sort of information, why not, first of all, we create like some sort of counter, like some sort of frequency lookup for T such that it maps A to 1, B to 1, and C to 1. So this is basically what is required. This is what is required in our window. Our window should have A as 1, B as 1, C as 1 at the minimum. And then maybe if we have a solution, then we can try to make the window smaller to see if we can maybe somehow make this better. Okay, so let's just currently start off with this and see where we can get at. So as always, in our sliding window type problems, we always start off at the edge, at the left-hand side. We always advance R to the end, and we advance L when we have a valid solution, and we want to essentially make our window smaller. Okay, so let's see how we can go about doing this. Well, first thing that we notice is that when we are over here, we have A, right? So here I'm just going to say my window, so I'll just name it W for window. And so here my window is just the letter A. Now notice that A is actually in T. And so if I was to take this A, then now suddenly I have one less requirement from this A here. Okay, so maybe we can record that. So maybe in T, what I can do is I can change this required of 1 to required of 0. Now, notice what this means. Well, this means that I only need to now look for B and C, right? I've already finished all of my A's, so I don't really need to look for more A's. I just need to look for B and C. And eventually, we might arrive at a scenario where we have something like this. We have something like this. If we have something like this, then what can we understand from this? Well, we can understand that this is a valid substring. This is a valid window. It might not be the minimum one, but it's definitely a valid one. So maybe let's, in the start, how about we keep track of the total amount of elements that we need to process, that are left to process before we arrive at a solution. So what do I mean? Maybe we can have some sort of like overall variable here, which I'll just call it overall. And initially, it's just equal to the length of this, right? Which is 3. Now, it's actually not the length of this, it's the length of like the amount, it's like the count of the characters that you have. So for example, if a becomes 0, then my overall will now be 2. I just need to process 2 more. And then eventually if these two become 0, then overall is 0, which means that I have nothing more to process. So then I can go ahead and form my window. But anyways, let's just take a look at how that can happen. So if a goes to 0, if any of these elements goes to 0, we basically have one less letter to process. So overall 2, this is also kind of like remaining. So overall 2 is equal to 2, which means we have 2 letters left to process. Okay, so let's continue. So then we advance R, and so now we're at A and D. And notice that we can basically just keep expanding our window here, right? Because D does not exist in this, but we're actually not at the solution yet. So we have no other choice but to keep going forward. So now we're at A, D, and 0, or A, D, and O. Now we are at A, D, O, and B. Notice B we can also decrease here. And so overall at this point becomes 1. Now we keep going, and now we're at a C. So EC, and notice here that C is also 0 now because we've processed the C. So now it is 0. Okay, so now overall becomes 0. So what does this mean? If overall is 0, then we are at a valid solution, right? So one of our solutions can be this. Now, what does this mean? Well, it means that if I was to increase R even more, then this is still like my best solution so far, right? So it doesn't really make sense to increase R. If I'm at my valid solution, then what I can do is I can decrease my window size. I want to try to decrease my window size such that maybe it can form a better solution, a smaller solution. So how can we go about doing this? When sliding window type approaches, the R will always increase the window size. So to decrease the window size, what do I need to do? Well, I basically need to advance this L pointer inwards. Okay, so notice when I advance this L pointer inwards, what happens? Well, first of all, I noticed that this A over here was actually required, right? It was required by T. So I can actually increase this back to 1, which basically means I still need 1A. And now notice that this is not 0 anymore, which means that we still need to process an A again, a valid A. So now I can increase this overall to 1, indicating that I still need to process A. I still need to process an A to arrive at a valid window. So now we can keep on going. So what is our window now? So now our window is something like this. And we can again add in the O, which we will add in. We can again add in the D, E, and then again we'll add in a B here. Okay, so now we added in a B. So notice what happens now. B, we don't actually need any more B, but we will still go ahead and update this to -1. Why? Because it means that we've actually added in 2 B's into the window. So what it means is that if we were to somehow maybe create some sort of window like this, it's still going to be valid because we already have, maybe we'll have 1 less B, so then this will be 0. So that's also a valid scenario here. So that's just something to notice here. If we have something like A, B, C, our window can still be something like, you know, maybe like A, B, AC, something like that, right? That's still a possibility. So that's why we can also do a negative here. Anyways, so we have this. We don't change our overall because these two we've already completely done. We've already processed them, so we don't change our overall. But we still need to increase our R because we are not at a valid window yet. So now we're at an A. So now what can we do? Well, now A becomes 0 here, right? And so now we are actually at a valid scenario, if you think about it, because all of these are either 0 or less than 0, which means we've already in our window added in all of the characters that we needed. So now overall is 0. And so my string now becomes this long string here. And notice that I'm actually not even going to add this because my current solution, which is this one, is actually smaller than this one. So I don't even need to add this, but just to kind of demonstrate, I will add it. So now what can we do? Well, given that we are at a valid window here, we can see if we can maybe somehow shrink this to form a better valid window. So can we do that? Well, let's see. We can move D here, so that's all good. We can move it here, so that's all good. Now, notice here, we're at the B, right? So what can we do? If we move this 1 more, then this B basically decreases by 1. It decreases by 1. Now notice that we're still valid here. We're still valid. This is still a valid solution because all of these are 0. That's why we keep track even if we go in the negative. So what does this mean? Well, this means that this substring here is still considered valid, right? It is still considered valid because it still contains all of the letters as part of T. It contains A, B, and then C. So this is also a valid substring. Okay? So if this is still valid, then what do we do? Well, if this is still valid, then can we see if we can maybe still decrease our solution? Sure, let's go ahead and see that. So I move it now here. So I was actually here. So now I'll move it here. Okay. So then now we are at C. Okay. And so this is still valid. This is still valid. Okay. So let's move one more in. So now a window is something like this. And now notice that our C, we actually require a C now. We require a C. So now suddenly our window is not valid anymore. So what can we do? Well, now we basically have to advance R again. So now we'll advance R to N, and we'll add in the N here. We'll advance it to a C, so we'll add in the C here. And notice that when you add in the C, again, this is 0. So if this is 0, which means this is a valid solution, this is a valid solution. And notice that we can decrease our window now to see if we can come up with a smaller solution. So if I do this, well then this is still valid, right? This is still valid. This is still valid. This is still valid, right? So this is still valid. Now notice if I was to increase this one more, well then we would actually not arrive at a valid solution anymore. But given that this B, A, and C is valid and it's actually smaller than all of our solutions so far, we will actually just create this as our solution. And then notice if I increase B, if I increase L by one more, well then this B count goes up by 1, this overall count goes up by 1. And actually at this point, we'll actually just end the loop because R will advance. And so B, A, and C will be our solution. So that took a while to explain, but hopefully you got the idea of like how we're going to use our minimum window here to go ahead and arrive at the solution. So let's take a look at how we can translate all of this into code. And as with a lot of these sliding window type problems, the code will be quite similar, but the questions will just be different. So let's take a look. Okay, so what are some of the things we need? Well, I mentioned that we want to know like how many elements are in T, right? So we can maybe just create a counter. So this will be like a dictionary mapping the letters to the numbers, like their frequencies. We also need maybe something like overall, right? And overall, I said it should be the length of C. So this will basically keep track of how many letters we still have to process, not the frequencies, but how many letters overall we still need to process. That's why I kind of named it overall. Okay, well, now we can create our left variable or right variable here. What else do I need? Well, I need to actually return a string here, right? So maybe I'll return my string here as res, and we'll return res in the very end, and now we're ready to begin our loop. So we always follow the same approach. So while R is less than length of S, and then at the very end, we will increase the R window, but now we need to process it. Okay, so initially, R and L are all the way here, right? R and L are all the way here. So we have this letter A here. So what do I need to do? Well, first of all, I need to check if I can even add it, like if it's in T, and if it is, then I can go ahead and decrease the count by 1. So I can check something like if S at R is in C, and remember C is like this mapping here, then I'm going to decrease the count of it. So C S at R minus equals 1. And remember, it's okay if it goes in the negative. That's completely all right. But now what I know is if it goes into 0, then overall I need one less character, right? Overall now I just need B and C. So I can check if C at S at R is equal to 0, then overall I need one less character. Notice that if it goes into negative, my overall doesn't change. It's only if it goes to 0 that it changes. Okay, so we've done that. Now, what is our valid scenario here? Well, our valid scenario, in which case we can actually form a window, is if overall is equal to 0. So actually overall starts off at 3, then it goes to 2. If it's equal to 0, then I basically processed all of these elements here in the exact amount that they want. Maybe not the exact amount, like maybe I have more A's than are needed, but it is a valid window. So I can actually check this. So I can check, what can I check? So I can check while overall is equal to 0. Then I know that I'm at a valid window. So let's go ahead and update our window. So I can do something like if, first of all, if res does not exist, then now we have a res to add. So I can do res is equal to S, and then the window would be L to R plus 1. So this is like the substring containing the text, right? So in this case, like it would be something like this. All of this would be added to res. Otherwise, if res does exist and the length of res, we can say is greater than like this, right? If it's greater than this, then we can again reset it to make res something smaller. So we can do, actually here, I can just do length of res, and then I can do length of res is greater than R minus L plus 1, right? So this is the size of the current window. This is the size of res. So maybe I can just put this the other way around. Maybe it's easier to understand. But basically, if the window length is less than the size of res, then again, I will update res to be this existing thing here. Okay? So otherwise, I can't really update res, right? I'm at a solution, but it is a bigger solution that I need. I'm already at a smaller solution here. So what can I do? Well, in this case now, I can basically go about shrinking my window, right? So I'm over here. Now I can basically go about shrinking my window and moving my left pointer inwards. Now, in order for me to shrink my window, what do I need to do? Well, I need to do L plus 1, right? L plus equals 1. I need to definitely do this. But before I do that, I need to actually check to see if the L that I'm moving inwards, if it has an element in T, right? Then I need to add back that element because I'm not adding it to my window anymore. It's being removed from my window. So what that would look like is if S at L in C, then again I will increase C, S at L. I will increase it by 1. Notice here I'm decreasing, but here because I'm removing it from the window, I will increase it. And then we can actually see if C, S at L is greater than 0, then I suddenly need a character, right? For example, here, A here now becomes 1 if I move this inward. But for example, if A was something like minus 1 and then we moved it inward, then it would just become 0, right? So my overall doesn't need to change. But because it was 1, but because it was 0 and now we moved it up, it becomes 1. Now suddenly I need another character. So now this Y overall increases to 1. And this is basically all we have. So here we are creating our window by moving our L or my RR outwards. Here, if the window is valid, then we'll go ahead and we'll try to shrink the window. And then we also update overall in this case. And here we'll update like the actual string themselves. And here we update the overall window. And so that's basically all we need to do for this question. Let's go ahead and run the test cases to see if they pass. Okay, let's go ahead and submit. Perfect, so we arrive at the solution. So this is an O of n time algorithm. It's also O of n space because we have the counter over here. But overall, it's a linear type algorithm and space. Okay, thanks for watching.